All right, then, great. Welcome back. Welcome to the third talk today about numerical simulation and the simulation branch of probabilistic numerics. This will be the second lecture about state-space model-based ODE solvers. And as someone that has been pretty excited about the subject for a couple of years now, I hope that Simo's talk left you all motivated, ready to go, ready to dive deeper into the world of ODE solvers. Who knows, maybe some of you are already making plans on taking these methods, maybe implementing an extended Krämer filter, and then using it to solve some challenging ODEs. Well, for those of you, I have bad news. So while the perspective on probabilistic solvers as GP regression or as external Krämer filters is absolutely crucial, it's not the whole story. There's still a long way to go, exactly in 90 minutes, coincidentally, until we can take these concepts from something that is possible to something that is actually fun to use. So what am I talking about? About 3.5 years ago, when I came to Tübingen as a freshly hired PhD student, I was motivated to learn everything there is about probabilistic numerics. Then I started implementing probabilistic ODE solvers from what I knew then, and I made a new friend. That new friend was the linear algebra error. So yesterday we talked about how most of you have worked with Gaussian processes before. I'm sure that almost all of those people know that feeling when a covariance matrix decides to develop a slightly negative eigenvalue and you can't actually do anything with it anymore. And now the blessing of sequentially computing those ODE solutions with a Krämer filter is that you can do it very efficiently. But this blessing is also a curse because you have way more of these covariance matrices that can decide to be numerically indefinite. So, and this is not the whole story. So this is called a work precision diagram. A work precision diagram plots usually the work measured in some kind of wall time, usually in seconds, against some precision, which is often some measure of relative root mean square error or any error measure that you care about. And we use these diagrams to evaluate how efficient ODE solvers are. Usually, the closer to the bottom left of this diagram your curve is, the better. For example, we see that this method, this dormant prince thing, whatever that might be, takes about 10 to the minus 4 seconds to achieve error 10 to the minus 9. And this is pretty efficient. The curve is almost horizontal, which makes sense because this is a really simple ODE we're solving here. Comparison, another algorithm called Hoyn, which is another ODE solver, is about 100, maybe 200 times slower to achieve error 10 to the minus 9. And simply from this diagram, we can conclude that on this problem that we're solving here, dormant prince is way more efficient than Hoyn. So why am I showing you all of this? In about the first 10, maybe 20 slides, I will roughly recap what Simo talked about, just in my notation. So yeah, we're going to change notation again. And even if we add a few performance considerations already, this is where we are. So we are pretty much 1,000 times slower than the already slow algorithm. And if we want to compare it to the efficient algorithm, then we're maybe 10,000, 20,000 times slower. And if you think about it, 10,000 times slower means that if you build this algorithm into a Markov-Chain Monte Carlo method, that means that for every sample for a probabilistic solver, you can compute 10,000 samples from a non-probabilistic solver. And while probabilistic solvers have good posteriors and they're very efficient for parameter estimation, that is really a race that I don't want to enter. So the main message of this lecture today will be how to get it from this 1,000 or 10,000 times slow algorithm to something that is way more in the ballpark of what non-probabilistic algorithms usually deliver. And in fact, I'm going to show you a few diagrams where we're actually faster than the dormant prince method. So now, let's get started with the actual lecture. All right, to recap the setup for a probabilistic solver in the state space model and the Gaussian process regression framework. We have some initial value problem. I usually use letter y. So the time derivative of y is equal to f of y plus some time constrained by initial value. And the way we go about solving these problems is we hypothesize that our solution is some sort of Gaussian process. We introduce a grid, And then we would like to compute the posterior distribution of y conditioned on satisfying these ODE constraints and the initial value. But since the ODE is usually nonlinear, this posterior is not Gaussian, it's kind of intractable, so we are happy with calling any approximation of this conditional distribution a probabilistic IVP solution. And every algorithm that delivers one such approximation, I'll say, is a probabilistic IVP solver in this context. And the beauty about this fairly simple approach of defining what the solution should be is that the same idea works for boundary value problems, it works for partial differential equations, for all sorts of strange and funky differential equations that you could think of. It is always very simple to write down the target, to write down what you want to compute. It is much harder, on the other hand, to actually compute it. So one of the main messages in Simo's lecture earlier was that if you use a Gauss-Markov prior, so if you use a Gaussian process that admits a state space representation, then we can use the whole world of Kalman filtering and Rauchtung-Schriebel smoothing to compute those solutions or to estimate those solutions in linear time complexity. And once we're done with this, then we get these uncertainty Gaussian process plots. So here on the left, for example, we're solving the Lotka-Volterra predator-prey model. There's this of oscillating dynamics of the number of predators and the number of prey, and then we have some mean, we have some samples, uncertainties. So we get the whole Gaussian process machinery. But how do we actually get there? Let's take a closer look at the prior distribution. So far, we assume that y is some Gaussian process. What we, in the context of solving differential equations, actually think about is we assume that it's a Gaussian process that admits some SDE formulation. So we say that our process y is the solution of this linear, time-invariant stochastic differential equation. And now let's remove some of the fluff on this slide, because we're going to transform it into something that is more practical to work with. So here, that's a higher order differential equation. To actually make the most out of the Markov property, we transform it into a first order problem. So we look at the stack of y and its first new time derivatives. And then we have a first order differential equation. So here, there's only the first time derivative. And of course, the matrices A become this companion matrix form, and the white noise enters only through the last component. So if we abbreviate this as the first order E dt of y is equal to A times y plus then sigma times b, we can actually use this SDE to implement our priors. And even though the whole setup works for general SDE priors like this, what we do in practice when we're solving ODEs is we actually only just use integrated Wiener processes. So the integrated Wiener process, or the new times integrated Wiener process, is the solution of the SDE I showed you before, but all the matrices A are 0. So we have that the new plus 1th derivative of y is basically equal to white noise. And the interesting bit about the integrated Wiener process is that it corresponds to spline models. So it's a very useful class of models which are super popular in, say, non-probabilistic numerical analysis. But the absolute main selling point of integrated Wiener processes are two. First one is that it has very few hyperparameters. There's only the sigma, nothing else, which is good because I don't really want to spend too much time with tuning hyperparameters at the moment. And the second bit is that we can implement integrated Wiener processes very efficiently. And this will be one major block that I will talk about later. So it's an amazing prior. Let's go back to the SDE. So the SDE of the integrated Wiener process, if we take this first order form, looks like this. So we have the first time derivative of y, and then we have the matrix A, which is this off-diagonal identity matrix, and we have the same B as before. And when we want to implement this algorithm, then what we do is we discretize it in time. So we need to look at the state transition between time t and time t plus delta t for some increment delta t. And for time invariant and linear SDE priors like this, we can write down the state transitions as some matrix vector product with phi, and then we have some process noise sigma. And for integrated linear processes, we can compute those matrices in closed form. So phi is this upper triangular matrix with with delta t and the delta t squared and so on in the upper half. And sigma is this strange Hankel-looking matrix which has weirdly high powers of delta t. And maybe if you remember that the state y tracks the original solution hypothesis plus its first derivatives, then you can maybe already see that what we're doing here is we're doing Taylor expansions. So we have our current state, which is bold-faced y, and then if we're multiplying it with this matrix phi, so 1, delta t squared half, and so on, then we're approximating y at t plus delta t with the second-order Taylor expansion. We're approximating the first derivative with the first-order Taylor expansion, and we're extrapolating the second derivative constantly. And in pictures, basically, if we use this to approximate, I think this was a weirdly flat sine function, then we get this quadratic approximation, so this green line, which growing uncertainty the further away we're getting from the current location. So the larger our steps are, the larger our uncertainty estimate. And how can we actually use this for computing ODE solutions? If we go back to our probabilistic IVP solution or our target IVP solution, then we use this representation as the stack of some state and its derivatives. And what we actually want to compute is we want to compute the posterior distribution over this whole stack of processes conditioned on or constrained by this ODE information. So we actually track some extra variables here. We track the time derivatives of our process plus this sigma output scale thing, this one hyperparameter that we have left. So let's simplify notation a little bit here, because on the next few slides I'll have a few equations. So again, we just look at bold-faced y, which is the stack of y and its derivatives. For convenience reasons, we only compute the IVP solution at the grid points, Tn. We can always reconstruct intermediate values by interpolating with that same hypothesis, with that same prior. Then we rewrite the constraint y dot equal to f of y as y dot minus f of y being 0. That's the variable that Simo called z. And since this constraint takes a lot of space, let's abbreviate it. Okay, so r is our ODE residual, the difference between the first time derivative of our function and the vector field evaluated at the 0th time derivative of our function. And now this is actually the posterior distribution that we want to compute or that we want to approximate. And we can always extract the top row from the bottom row, but the bottom row is much easier to work with. All right. So what's next? What's the next step in implementing these ODE solvers? Well, we know that our prior has the Markov property, so that means that we can also factorize our posterior distribution into some initial distribution, which is the terminal value solution of our IVP, plus a series of backwards transitions, and I'll elaborate on that in a bit. So essentially what we're building is we're building this hidden Markov model type thing where we have our variables y at 0, 1, and so on, and we have some ODE constraints, and from knowing the joint distribution between y0 and y1, and then y1 and y2, and so on, we can compute extrapolations, we can compute backwards transitions, we can compute all sorts of things. And the same from the joint distribution or any approximation of the joint distribution between y0 and the ODE. We can do corrections, we can compute likelihoods, we can do all sorts of things. So, important bit here is that the first term in our product expansion is that we have the solution at the terminal value. So we have y at Tn, so T capital N, constrained by the residual evaluated at all time points. And then we have a lot of backward transitions, which are only conditioned on the previous observation, so we have little n here, plus whatever is left in the future. And since it's always a bit tedious to remember equations, you can think of it as this. We have one term that we simulate forward in time, and we have a lot of terms that are kind of byproducts of this forward simulation. And the solution at the terminal value is basically always of interest, and the ones and the other backward transitions are only relevant if we want to, say, smooth the posterior, so if we want to access the ODE solution at some intermediate time point. For example, to make those plots that I showed you earlier. So the basic message here is that the ODE solution factorizes into a bunch of sequential rules or joint distributions. So what does that mean for our ODE solver now? For our ODE solver, that means that we start by initializing the boundary condition, or in this case, the initial condition, and the first time derivative. So we start at time 0, and then for all time points, we iterate between extrapolating from the current time point to the next time point, which is a process that computes the marginal of y at tn plus 1, condition on all previous observations. So again, here's little n. But in this step, we can also compute the distribution of y at tn, conditioned on potential future observations. At this point, we don't have it yet, but that's something that we will use for, say, smoothing, or if you want to sample from the posterior. And it only depends on quantities that are available at this stage already, so we might as well just take them and make our life a bit easier for when we're done with solving. Once we're done with the extrapolation, then we need to linearize our ODE. Our differential equation is nonlinear, and this kind of makes the whole process a bit annoying. So we approximate it with something tractable. Usually that is some matrix vector product plus a bias term. I will discuss this in a bit as well. We use this approximation to approximate the conditional distribution at tn plus 1 conditioned, and now we have the new time point. We see that? Yeah. So now we have tn plus 1. So essentially what I'm describing here is a Krämer filter, or external Krämer filter. But there are a few differences, which I will show later. So once we're done with this, we can use our solution. We can use our already factorized representation of the solution to do parameter estimation, to just compute samples, to just plot means, or do whatever you want to do with those IVP solutions. So how does this tie into what Simo talked about earlier? The connection is that we start with some prior distribution. Here we have, I think it's twice integrated Wiener process. And we iterate forward through time, always computing those filtering distributions, which are conditioned on all previous information. But you can see there are little jumps, and the whole process is not very smooth. So once we are done iterating through time, then we have our complete characterization of the solution, and we can, for example, marginalize backwards, or we can sample from the solution. So what does this have to do with Krämer filtering? If we ignore computing those backwards transitions, and if we just take the initialization, the extrapolation, and the correction, assuming that our process or that our problem is linear, then we get exactly what the Krämer filter would do. Similarly, if we include the backwards transitions, then we're in the world of smoothing. So essentially, if we just add this one computation to the extrapolation, and we actually use it to marginalize the solution over the grid points, then we get what the smoother would do. And this question can be pushed much further. So for example, Simo mentioned a lot of extended Kalman filters and unsettled Kalman filters. And in the end, that is just a matter of linearizing our ODE model correctly, or in different ways. And if we linearize this with the Taylor approximation, then we get extended filtering. And if we do other things, then we get other filters. But in the end, it's all a question of linearization. And maybe some of you are familiar with the connections between nonlinear filtering and Gauss-Newton methods. So if we take this linearization correction step and we keep iterating it, so we keep re-linearizing at a solution, then what we're doing is we're doing some local Gauss-Newton scheme. If we use some non-Taylor-based linearization, then it's something slightly different, but it's essentially the same. So we can just use our solution to improve linearization and repeat. There's just a million variations of what one could do here. Once we're done with everything, we can use the posterior to do, for example, parameter estimation in the ODE, which is something I'm going to talk about in the final block of this lecture. What if our ODE is not standard, so not first order, but say second order? What do we do differently? Well, the only place that is affected by this change in ODE is the second initialization, so the first time that the ODE residual comes into play, plus the linearization. So we only have to linearize differently, and then we again have the same solver. It's the same algorithm. It's always the same idea. Similarly, has anyone ever seen an 8th order differential equation? So 8th time derivative equal to something. You have? Okay, that's good, because I haven't. I have no idea. But if you gave me one, then we could solve it. So in the only place, again, that would be affected would be the second initialization and linearization. And that's all a question of, like, if you give me some weird and strange differential equation, the solver remains basically the same. Similarly, can we solve non-ODE-based initial value problems? Say, what if we are looking at a mass matrix differential equation? A mass matrix differential equation is of the form m times time derivative equal to some vector field. And the issue is that this m is usually singular, so we can't just invert it and pull it to the other side, but we have to solve it as this. And now, what is different again? We just linearize differently. Again, our initial information, so the first grid point information is different, linearization changes, the rest is the same. And we could keep playing this game, we could keep coming up with weird differential equations, and no matter what you're giving to me, I'm going to tell you that point 2 and point 3.2 are going to change, the rest is always the same. And we can push this even to non-initial value problem data. So what if we are solving, for example, boundary value problems? A boundary value problem is a differential equation with a constraint on the left, so y0 is constrained and y1 is constrained. And this is some strange non-local behavior because we can't really step forward through time anymore because we need to enforce boundary information. But luckily, it's still kind of the same algorithm. Now we just initialize the different boundary conditions, so we don't just get y0, we also add y1 into the mix. And this step is different now. We linearize outside of our time loop. So in the context of what Simo talked about earlier, we're doing some global map estimation. We don't iterate locally, but we iterate the whole process. And then we just extrapolate, correct. Since now our model is linear everywhere, we are just basically in the Krämer filtering world, and then we just re-linearize and repeat until we're done. Okay, so what was the point of this? So now basically we have this template of these 5 or 6 steps, and we can use it to build, I don't know, 2 million different ODE solvers. But there's one catch. So everything I've said so far basically says how the ODE solver is a filtering problem. But it's not. And there's one big difference, which is the time step. How do we choose our grid? In the definition of our solution, or in the explanation of what our target is, we always assume, give me some grid, and then we have this posterior distribution that we want to compute. But how do we get our grid? Well, usually ODEs are solved adaptively. That means we start at time 0, and then we iterate through time, and we always accept and reject steps until we're happy with some tolerance. So we want to find some grid that ensures that all local errors, and local is in quotation marks here because you don't really know what local means, it's just a very specific error definition, should be equal to some tolerance. And if we have made a step, if we have an error estimate, and we know that the error at time t plus delta t is too large, then we basically reject our step. So the whole concept of the step is that we need an error estimate. We assume that the local error decays as some polynomial of the step size. That is important, but that is usually something that you can derive on paper before going to your ODE solver implementation. And then by scaling our new time step with tolerance divided by error to some power involving this local convergence rate, we can kind of guarantee that the next step will be just sufficiently small to achieve our tolerance while still being large enough that we're not wasting computation. And this procedure, as scaling the old time step with this tolerance error ratio, is called an integral controller. In practice, what we often do is we use a slightly more sophisticated version of that, which is a proportional integral controller, which kind of adds a little bit of momentum into the mix. But that does not really make or break the probabilistic ODE solver idea. The point is just that we need to estimate our error locally, and then we refine our grid while we're stepping through the solver. And that's not just something that we're doing because everyone does it. It's not kind of like algorithm peer pressure, but it is very important. So we replace kind of this for loop idea of going over all time step with this condition that while we are not done yet, we just keep generating steps. We keep extrapolating, linearizing, and correcting, but then at every step, we also need to estimate an error. We need to accept or reject it, and then derive a new step that we're taking. And for some differential equations, we can't solve anything without stepping through the solution adaptively. So look at this Van der Pol system, for example. That's a textbook example of a stiff differential equation. And it's usually stiff because this number here is fairly large. If this were 1 or 10, those problems would be much nicer. And we see that in the Van der Pol solution, we have these weird spikes. And they already look pretty weird in this plot, but the figure is actually clipped. They go up to like 10,000 or 100,000. And we notice that our ODE solver has to take incredibly small time steps at these peaks. So here it's taking time steps of 10 to the minus 8, 10 to the minus 9. Whereas if we were taking those steps for the whole time domain, I guess the code would still be running. And the figure is 2 years old. So we can't take like 10 billion time steps, but we need to be very careful with our budget, because in order to resolve those strange spikes, we need very small steps, but we only want to use it there. So for many ODEs, for many initial value problems, adaptive steps are actually not a choice, they're a must-have. And this is one of the factors that distinguishes the way that we're actually building probabilistic ODE solvers, that we're implementing them, from maybe traditional external Krämer filtering literature. So back to the original problem. So far, everything was still very close to the previous talk. Now, what do we do about our linear algebra errors? We still have a lot of covariance matrices floating around, and we need to do something about it. And this is why, in the remaining block of this lecture, I'm going to go through each of those areas, and I will explain how we actually, what the details are and what the necessary steps are to make each of those components sufficiently stable and sufficiently fast to get an ODE solver that performs really well in the end. So we'll start with initialization, then we'll talk about extrapolation and how preconditioning, which is something that we've already seen yesterday a little bit, is absolutely crucial to generate high order, so high derivative integral Wiener process priors. We'll have a closer look at linearization, and I will briefly touch on how to do square root updates with Gaussian variables, even though that is a subject that I think will be covered in more detail tomorrow in the workshop. So, are there any questions so far? Yes?
What do you do with the rejected steps? Do you use them?
Yeah, you just throw them into the bin.
You throw them away?
Yeah.
So you use them?
maybe you could, I don't know how, but if you have a good idea, that it could be something, yeah? No, like in principle, of course, you would like to reuse this information, but in the ODE solver context, it's quite common to just say, okay, that was too large. I mean, in the end, you're generating information that could not be used, which is why you reject it. So I'm not sure whether there's actually a way of incorporating it sensibly. But there might be something. Yeah?
So you mentioned a problem where you apply a linear transformation to the left-hand side of the ODE.
Yeah.
This matrix M could be
Yeah.
non-invertible.
Yes.
Wouldn't this lead to an ill-posed inverse problem?
That's not necessarily an inverse problem. So we're still talking about solving ODEs. And then we're not so inverse problem is basically, or like maybe rephrase it as a parameter estimation problem, that we're not really estimating parameters yet. So it's still an ODE, and of course there is like the question of whether this problem has a unique solution. But if it does, this is how we would solve it.
So if you are estimating the parameters, then this matrix M setup would require an invertible matrix.
Well, usually in those contexts, this M is given. So it's often some, think of a diagonal, so some identity matrix where one of the diagonals is 0. So you have some differential constraint on the first two states, and then maybe some algebraic constraint on the last one. But that is usually given. Yeah?
Yeah, I have a very general question.
Mm-hmm.
So I say, for example, if you want to ordinate differential equations and you use this probabilistic approach, you get uncertainty.
Mm-hmm.
Then there's very general classical approach, find the methods, and what is in generally will be disadvantage compared to these classical methods. Okay, advantage is uncertainty, or will be like
So you mean the disadvantage?
I'm missing this some point. I say it's advantage uncertainty, but or will be disadvantage, something like that.
So are you asking about the disadvantages of
Yes,
using this probabilistic setup?
takeaway, you getting advantage by uncertainty or will be disadvantage. Like, I'm not sure it could be wrong question, but
Yeah, like I'm not sure how straightforward that is to answer. So of course, since we're doing some sort of Gaussian probabilistic regression, there will be some discussion of if you want a covariance that is useful, it comes at a price. I mean, at least you have to store the values in that covariance, and if it's big, then it's big. And so that could be phrased as a disadvantage, but in general, I don't know. I think these solvers are great. Don't think that's a disadvantage. Yeah?
You mentioned this analogy with the classical solver when we have stiff problems and then we have to adjust our time step.
Mm-hmm.
But in classical approach, we only do this for stiff problems. So like we can also switch to implicit schemes,
Mm-hmm.
avoid this. But
Mm-hmm.
in this approach, I guess we should always adjust our time step. Like
No, I'll postpone this because it will come up again in a few slides.
And following up this question, like the previous one, maybe there is this disadvantage that it's more difficult to analyze such kind of methods. Or like from like my point of view, it would be more difficult to analyze like stability or something like that.
Well, I mean, okay, so this is, of course, this is subjective, but these methods, they're not coming out of nowhere. So since we're in the Gaussian process world, we have connections to reproducing Hilbert spaces, and we can use a lot of machinery there. And if we want to talk about stability, again, that's coming up in a bit. Then there's also the filtering world that we can borrow a lot of information from. So they're not necessarily harder to analyze, depending on what you know, of course. All right, so let's move to the first concrete initialization step. So what are we doing? Let's say we have some initial Gaussian distribution for our SDE prior. For example, think of a standard Gaussian, but in fact you can use anything. Any well-defined multivariate Gaussian distribution will work because whatever you choose here as a value will be irrelevant later anyway. So what are we doing when we're initializing? The first information that we're incorporating is the initial value of the ODE itself. So we have y0, which, and that can be shown, defines the first element of your mean to be exactly this y0 because we have a constraint. If we had observation noise here on this information, then we would not be exactly y0, but everything is constrained, so we have our value here, and we have lots of zeros in the covariance matrix. Now, if we initialize the first ODE information, so the first residual, then we have the vector field evaluation as the second state. So we know from the ODE that the time derivative is equal to the vector field evaluation. And again, one can show that we get exactly this state of elements. Here star is always some undefined value. It's not necessarily the same one between two slides. It's just something that floats around. OK, so that gives us a good starting point for our simulation. But what's next? What about those two values? Well, if we're being clever, why don't we also enforce the time derivative of this residual at this point? So we know that the first derivative of y is equal to f of y. Then, yeah, I mean, many of these methods we need Jacobians anyway, so we might have already computed it somehow. Let's use it. And we can also constrain our prior on derivative of r being 0. And then in this third element, we get some Jacobian, the vector field times f plus some time Jacobian, which is always a factor that I see, and then I regret that I didn't assume my ODE was autonomous. So this is also floating around. And now, if you're a little bit like me, then this is the point where we're getting greedy. So we have our first three elements, but there's one left. And this one is a bit annoying because now we don't really know what to do with it. Like, we have Jacobians, maybe we need higher derivatives, but I would really like to get rid of this one final star in our covariance matrix and this one final unknown, because then we have an exact initialization of our state space, and that is not just nice for people that want exact information, but it's actually super useful for stability in our implementation. So how do we do this? Well, so far we know that y is the initial value, the time derivative is f of y0, and we know that the second time derivative is equal to the Jacobian of f times vector field plus this extra term here. So what can we do? Well, we can differentiate again. So let's remove some of the fluff in this equation. We know y0, we know f is always evaluated at y0 and t0, and we know that the Jacobian is actually a linear operator, so we write it as 1. The Jacobian is a linear operator, the Hessian is a bilinear operator, sorry, the second derivative. And then we actually need this because in the end we'll have lots of matrix, vector, something multiplications. So this will make it a little bit clearer. If we differentiate that equation again, then we know that third time derivative is, and now we have the Jacobian of the Jacobian evaluated at f of y and f of y, so that's a bilinear form now. And then we have the Jacobian evaluated at the Jacobian, and then everything gets super nested. So in the end, we know that the nth derivative of our initial condition is equal to the n minus 1th derivative of f composed with y. So we're building this new function f of y of t, which is a function of t. And then we can use the ODE to relate our derivatives of y to the derivatives of this new function. And already we're building states with these high derivatives. We had the connection to Taylor series earlier. In the end, what we're saying is that the nth Taylor coefficient, so the nth unnormalized Taylor coefficient of y, is equal to the n minus 1th unnormalized Taylor coefficient of f of y. And this is useful information because now we're in the world of Taylor series. And Taylor series also, that's something that we understand computationally. So if we have a function that can generate Taylor series of other functions, then we can use it to recursively define all of our ODE derivatives. So if we have a function, say a, that takes some f plus some final Taylor series of y, and it kind of cheaply returns some Taylor series of the output or of the composition of this function, then we can start by plugging in f and our initial condition. Then we get the first derivative, and then we take this guy, move it back in here, because now we have a first order Taylor series, call it again, then we get first and second derivative, and so on, and we can recursively build up to, I don't know, 10, 15, 20 derivatives which can be cheap provided this function is super cheap. And of course, I mean, now that everything is possible, like PyTorch, JAX, Julia, and so on, we immediately think that, okay, autodiff works. But if we go back to this slide, then we can already get a feeling for when we differentiate terms like this one splits into two summands. So we have the product rule of differentiation. We do it again, then this one will split into, how many will this be? Three summands and so on. So in the end, we'll have an exponentially growing number of summands if we just compute naive automatic differentiation. But luckily, there's something called Taylor series differentiation, which essentially, and this is a little bit orthogonal to what I'm talking about here, which essentially knows that all of major Jacobian vector products are pointing into the same direction, which allows us to simplify lots of internal representations. Then we can compute terms like this, not only sub-exponentially, but often linearly in the number of derivatives that we're building here. And if you're a little bit like me, then you're glad that these functions already exist. For example, there is an implementation in JAX. There's also something in Julia. And that is something that is super useful for when we're actually building ODE solvers. So every time you're thinking about high-order integrated linear processes, and you have an initial condition that you don't really care about the value of, it's always a good idea to take this Taylor series perspective seriously and to try to initialize as many derivatives as possible. Okay, and now since it's been roughly 45 minutes since I started, how about we take a quick 2 to 3 minute break? Let's see whether it's actually going to be 2 or 3 minutes. So we'll have a bit of water, maybe stretch out a little bit, and then we'll continue in a couple of minutes. Okay, so let's pick up where we left off. Initialization, high-order derivatives. We know the ODE. We keep differentiating both sides. And then, assuming someone gives us this autodiff engine A, then we can recursively compute all high-order ODE derivatives. And what that gets us is that now we have our state vector with y, f of y, and then Jacobian, and so on. And there's still this last unknown, but we can just use this one function, iterate 3 times, and we suddenly have y, and we have first, second, and third time derivatives, and we have a zero covariance because we know all of our states exactly. So that's initialization. Every time we're initializing these ODE solvers, we're trying really hard to get as many of the Taylor coefficients exact as. And now, with initialization, we can actually use this really good starting point where we know a lot about the solution already and start iterating. Okay, so let's move from initialization to the first extrapolation. On an earlier slide, I showed that the conditional distribution of this big state vector bold y at t plus some time increment, given the previous state, has this affine Gaussian noise transformation with phi and sigma. And phi and sigma are these Taylor coefficient matrices and this symmetric Hankel style matrix here. But you can already see that the sigma is a little bit weird because there's the 4th power of the time, and if we go up to not 3 derivatives in the state, but maybe 8 or 9, then we suddenly have 9 or 10th powers of the time, and that just can't be right. So this matrix is a little bit strange, and it gets worse the higher the order of our method becomes. So what happens? What happens with that matrix actually? Every time we're extrapolating the covariance, we're computing matrix products and sums of the form phi times covariance times phi transpose plus this process noise. Okay, that's just Gaussian marginalization with our prior, with our discrete time integrated Wiener process prior. But the thing is that our covariance matrix C estimates the error of our ODE solution. And what happens if we have a really good ODE solver? Then C is basically 0, or at least we want it to be small. We want C to be as small as possible. So what happens a lot, for example, in the very first step after initializing our solver, is that we're computing 0 plus sigma. That is our process noise. And now the annoying bit is that if you're familiar with how smoothing works, is that this matrix has to be inverted to compute something called the smoothing gain. And the smoothing gain is important to sample from the posterior, for example. But how do we invert a matrix that looks like this? So we fourth power, third power. You see there's this weird anti-symmetry here. And matrices that look like this are famous for being extremely ill-conditioned. So what can we do? Well, one important observation is that yes, sigma is anti-symmetric, and it's not really low rank, but there is a lot of row and column structure, so maybe we can make use of this information. So what we can do is we can split sigma into the product of some time, so we have delta t squared, delta t and 1, times some constant matrix, here this 1/5, 1/4, and so on, plus sigma transposed. And if we do this for sigma, and if we do the same for phi it's a different transformation, which involves the inverse of the diagonal matrix, then we can split the extrapolation formula for the covariance into some coordinate transformation t on the outside, so t and t transposed, and then everything else basically happens in a different space, in a rescaled space. We are rescaling our coordinates. So here, delta t squared, delta t and 1, if we go back, then we can basically extract it from this to the power 4, to the power 3, and to the power 2. And everything that we're left with is a constant matrix. We still have the same anti-symmetry structure, but now at least all the elements are on a roughly similar scale. So instead of going from delta t to the power of 4, 5, 6 up until to 1 on the diagonal, we are roughly in ballpark order 1 at this point. Okay? And now the good thing is that if we're looking at this covariance matrix C and say we want to invert it, then we know that the inverse of the C is the product of the inverses of those matrices. They're all invertible. But since our coordinate change is diagonal, we can do this in closed form. So this knowledge that we have these powers of t, of delta t, and these kind of mess up our inversion of the covariance matrix, this problem is completely gone because we just do it on paper. And instead, what is left is inverting a matrix that is, or like solving a linear system with a matrix that is proportional to this matrix. And that is something that is numerically much better posed. And this whole concept is essentially a coordinate change in our state space model. So if we change our coordinates from our state and derivative coefficients to, and now t to the minus 1 times our state, so t inverse here, state, then if you now squint a little bit and then you pull out some delta t information, then you can roughly get a feeling for what happens to our state. So if we divide this matrix, everything in this matrix, if we multiply everything in this matrix by delta t squared over 2, then here there's a 1, here is something that is roughly delta t, and here is something that is a bit larger. So what are we doing is we're essentially switching from unnormalized Taylor coordinates to normalized Taylor coordinates. So we're changing from just tracking the derivatives to tracking the whole summands that we are using when we're doing Taylor expansions. And for integrated linear processes, this coordinate change removes all dependence of the process noise and of the system matrix phi on delta t. So every step is basically equally well conditioned. And no matter how large or small our step is, the step size will not be a problem anymore. Questions? Yeah.
Does changing degree have an impact on the efficiency? Do you have to sample exponentially more your delta t squared third power?
Okay, that's a really good question. Actually, the impact of this change is positive on the efficiency. So the reason is that now these matrices phi 0 and sigma 0 are always the same at every step. So we can compute them once. We can Cholesky decompose them once, we can invert them once before we actually start the simulation. And every dependence on the step size is now some diagonal matrix. And if we look at working with diagonal matrices, when everything is dominated by covariances, so usually dense matrices, the costs of inverting T or multiplying with this matrix T is basically zero compared to all the other matrix operations. So this bit doesn't hurt, but the ability to pre-compute the system is actually very beneficial. So it makes the implementation faster usually rather than slower.
But the number of samples increases exponentially with the degree?
Which number of samples?
Sorry, the size of the grid.
The size of the grid? No, this is independent of the grid. So like this is assuming that we have some grid or that we have already selected our grid, because we basically know that we want to extrapolate to C at t plus delta t. And the equation here and the equation on the previous slide with just phi, C, phi transpose plus sigma, they're doing the exact same thing. We're just separating it into this product and use this to compute inverses of covariance matrices efficiently. But everything else is completely equal. Okay, so extrapolation, again, it's a very frequent thing that we encounter here. We're doing some integrated Wiener process stuff. We see a Taylor series. We take it seriously by switching between normalized and unnormalized coordinates, and we suddenly gain a lot of efficiency. So what's next? Talking about Taylor series. So usually in interesting applications, our ODE is nonlinear. So we have some nonlinear vector field F, and the most obvious way maybe to make this tractable is to just say, okay, we linearize it. You know, we do a first order Taylor series expansion of F around some, okay, this y0 is, yeah, now that's the linearization point. It's a bit, that's not very good. That's not always the initial value. It's just some points. We linearize F around some y0 here, and then we have an affine transformation instead of a nonlinear one. And once we're in the world of affine transformations, we're in the world of closed form Gaussian inference, and we can compute everything. Instead of Taylor linearization, we can also treat this completely statistically. So we know that when we linearize, we usually linearize around some local estimate. Often it's the result of the extrapolation, but that's a distribution. So that's a Gaussian distribution. Instead of just linearizing around some state, we can basically linearize around the whole distribution, and that is then called statistical linearization or statistical linear regression. And it also yields an affine transformation of some state. It's just that the bias here is a Gaussian random variable with a mean and a covariance. And among some other things, this covariance encodes basically how certain our linearization point is. So if our linearization point is really bad, but we know this and we have a massive covariance, then what this is going to do is it's going to inflate the whole uncertainty, and the linear regression will still be bad, but it'll be uncertain. And once we're done with this, then we replace our residual R, so our ODE residual y dot minus f of y, with this affine expansion. So we have y dot, which we just leave. We don't touch it. We only linearize the ODE vector field, minus hy minus b, or if we have a second order differential equation, then we have a vector field that depends on y and y dot. So we compute this residual y second derivative minus, and then we have two linearization matrices. And now the game continues again. So we have a mass matrix. So what is our information? Our information is m times y dot minus whatever is left from linearizing the vector field. So essentially, once we've linearized our vector field, the whole problem becomes tractable, and we can actually compute solutions. So we plug it into the solver. If we want to, we can iterate. We don't need to. And then we're good to go. Again, this is basically what Simo explained earlier with his filtering, the filter explanations. So if we linearize with a Taylor series, then we're in the world of extended Kalman filtering or smoothing, depending on what we do with it. Statistical linear regression then leads to, for example, the uncentered Kalman filter. But everything on this slide is known to you already. But now we're moving to something that is a little bit unorthodox, maybe, from the perspective of a filter, which is we can also do 0th order linearization. And that might sound like a completely ridiculous idea. So we have a function and we approximate it with a constant, both with a Taylor series or statistically, which then gives us this very simple observation model. So we have the constraint y dot minus b or y dot dot and so on. So we always have some constant approximation. But this is something that has worked extremely well for ODEs. So that's basically one of two very common ODE solvers that we're using all the time. And 0th order linearization can, just like 1st order linearization, be just plugged into the solver. And if we want to, we can even iterate that. This is like now getting a little more niche, but for example, it has been pretty popular to use it for computing geodesics, so distances and manifolds. Okay, so linearization, which is like weirdly, since the main point of the blocks before that was that we have a Taylor series and we have to take it really seriously, weirdly the linearization bit is the one where we care the least about Taylor series. So yeah, 0th order, fine. 1st order is good, 0th order is also fine, as long as we know what we're doing with it. So what's the main difference between 1st and 0th order linearization? The main difference is that these solvers have different stability properties, which ties into your question earlier. So usually when we're in the world of ODE solvers, and we know that if we have a Jacobian, then the algorithm is likely to be one of the more stable ones. And the same is true here. So we know that we have a Jacobian, then we are in the world of 1st order linearization, and we know that this kind of solver is astable, which means that it solves a certain linear test problem exactly. And astable algorithms are really useful for stiff differential equations, like the van der Pol equation that I showed you earlier. So for example, in this figure here, we're taking the van der Pol equation, and we solve it adaptively to some tolerance 10 to the, I think it was -5 or -6. And we just assume that this tolerance has been reached, and we vary the stiffness of the problem. So it has this one free parameter mu, that if we increase it, the problem becomes more stiff. So it becomes harder to solve. And if we compare a bunch of different approximation methods, so all the 0th are doing 0th order Taylor linearization, and the ones are doing 1st order Taylor linearization, then we know, then we can see that the 0th order methods are taking a lot of steps, even for comparably small difficulty parameters here. So the figure that I showed you earlier was at this point, which like we wouldn't even be able to get close to with a 0th order method. However, with a 1st order method, then the number of steps grows a lot more slowly and a lot more predictably with the difficulty of the problem. So roughly speaking, 1st order methods are really good for stiff problems, or in general, if you're not sure how stable your solver needs to be for your problem at hand. On the other hand, and we're going to see this later, is that the 0th order methods are extremely fast because they're factorizing the function so aggressively that we end up with a state space that is much smaller than what we might actually expect it to be. So this is about linearization. And while linearization is an important part of this whole algorithm, and then it doesn't really solve our problem of still running into indefinite covariance matrices. So yes, we had covariance matrices, yes, we've done some preconditioning, but, and now back to your experiences with Gaussian process covariances, we know that sometimes the sum of two covariances just isn't a valid covariance matrix anymore. On paper, it is, but in practice, I guess it's happened to all of us that we suddenly get something super weird. For example, we could have very slight asymmetries in our matrix, which sounds like no problem, but even for the slightest asymmetry in the matrix, Cholesky decompositions don't work anymore. So we need to find a solution for that. And the solution to making sure that sums and products and conditionals and so on of covariance matrices remain valid covariance matrices is to use the fact that a covariance matrix is positive semi-definite or even positive definite which means it has some kind of generalized Cholesky factor, so some kind of matrix square root. And we're trying to write down the whole operation only with the square root C of the covariance matrix. And this is actually possible. For example, we can compute the sum of two covariance matrices purely from their Cholesky factors by QR decomposing the stack of those Cholesky factors, which yields R transpose R equal as the inner product of those matrices. And we see that, okay, that is C1 square root times C1 square root transpose plus C2, C2. So we have C1 plus C2 again. So the sum of two covariance matrices can always be computed in square root arithmetic. And the same is possible for conditional covariances. So the Kalman gains, the inverse Gram matrices, and so on. So this factor P minus K as K transposed. But I'm going to postpone this to Wednesday to Fatime. I don't know where she is, but I'm sure she's going to talk about this tomorrow in detail. Okay, and as a result, and now this is a little bit underwhelming because I would love to show you some colorful plot how everything works now, but it just works. There's nothing to show. So now once we actually moved to, after preconditioning, after initialization, we moved to square root arithmetic as well. All of our stability problems were gone. Well, all of the numerical stability problems. So that is absolutely important. And the same, I guess, is true for Kalman filtering and smoothing. So you have the world of square root filters and square root smoothers. And I suppose those are also super useful, but especially with these high order integer Wiener processes and these noise-free or very low noise constraints that we're having, the whole numerical aspect is becoming so brittle and a little bit weird that it is really important to make sure that we always have valid covariance matrices. So in summary, we have preconditioning, we have good linearization, we have initialization of all derivatives, and now we have square root arithmetic, and those four blocks together give us a useful ODE solver. So to summarize, we have the initialization bit, and then while we're not done yet in time, we keep stepping forward. We always extrapolate, we always linearize, correct, and then we do our error estimation, acceptance, rejection bit. And if we do all of those steps in the way that I just explained, then, well, I don't want to guarantee it, but I can confidently tell you that it's probably going to work really well, even if you go to high orders of your prior. Questions so far? Yes?
If you solve your ODE and instead of now having an exact initial value, you say, okay, it's also as a Gaussian distribution, and you would like to initialize it, can you somehow also initialize it with, say, the right uncertainty? Just by, I mean, since derivative is also linear, somehow I guess it should work.
Okay, so basically you're asking if this whole Taylor series differentiation argument also works if your initial value is uncertain. Yes and no. So yes, in the sense that you still have your equation, and you can just keep differentiating both sides. And what will happen is that you'll end up with some, like you will basically keep calling your differential equation. If we go back to this slide here, then all of these terms will always be matrices. So Jacobian times something is always a. So basically the ODE itself, these terms will be gone. So we can define one such recursion, yes. However, it's not really clear to me whether these methods still work. So if it's linear, yeah, you can still write it down, then you get your distributions over everything. But if it's nonlinear, I don't know. You can probably get away with some clever linearization, but I'm pretty sure that you can't just call jacks anymore. Something else? Okay. So now, since we've been through all of these small bits, where are we now? So now we're done basically considering the stable implementation of these solvers. So let's go back to the slide that I showed you in the beginning. So I showed you this problem where we have this one solver here that is kind of parallel to Hoyne's method, but 1,000 times slower, and we have the one that is more parallel to Dom and Prince, and like 20 times slower maybe, something like this. And from the lead up to this, you can probably guess now what the difference is between those methods. One tracks one derivative, and the other one tracks 4 derivatives. So now we're actually able to go to higher order methods, which will give us faster convergence. And in fact, we can go much higher than 4. But first of all, on this problem, it's not really necessary. We can see that the curves are already horizontal. And second of all, then it becomes a little bit harder to compare because there are not that many non-probabilistic methods around in Python implementations that can go to higher orders than, say, 8. So on this fairly small problem, we're good to go. But while it works for, like, I think it was a 1 or 2 dimensional problem, what happens if we go to a slightly harder one? So here we're looking at the so-called Pleiades problem, which describes the motion of, I think it's 7 stars, and they're floating around in a plane, and that's a second-order differential equation, which is 14-dimensional. So 14 dimensions is not quite high-dimensional yet, but it's sufficiently high-dimensional to be really tedious for Gaussian process models. So what happens here? Well, we're basically back to square one. Again, we see that Dom and Prince, which is a 5th-order method, is fairly efficient, so it takes about 10 to the minus 2 seconds to achieve 10 to the minus 7 error, more or less. And our 5th-order method is, again, 1,000 times slower. And why is this? Well, it is because we're doing sequential Gaussian estimation, which depends cubically on the dimension of the ODE. And cubic dependency on something that is like of ballpark 10, 20 does not mean we can't solve it. It just makes it really annoying because it is only just slow enough to not be really competitive with other methods. So what's missing? Turns out that I've not told you about one final component of implementing those solvers, which is what are we doing with our covariance matrices? Do we actually have to track all correlations between all states and all derivatives? Well, maybe there are problems where we need to do that, but for most problems, it's not necessary. And it turns out that if we assume that our process noise covariance matrix is block diagonal, and if the linearization is, think of it as sufficiently nice, then all posterior covariances are block diagonal, which means we can basically implement this ODE solver step for each dimension independently. So we extrapolate a one-dimensional model d times, we linearize, and then we correct d one-dimensional models again. The same is true if instead of block diagonality we enforce some Kronecker structures. So if we enforce that the covariance matrix is the Kronecker product of something nu times something d times d. And if the linearization preserves this structure as well, all posterior covariances have the same structure. And this is useful because it means that we can implement block diagonal models, so those block diagonal models, in linear complexity in the dimension. And for these Kronecker matrices, we can even go one step further, and we can implement them also in linear dependence in the dimension, but with a smaller coefficient. But which linearizations actually preserve this structure? So it sounds a bit like a strange assumption. So if we think about it, then a block diagonal process noise basically means that we're stacking d independent Gaussian processes on top of each other. But how does this tie into the first order, 0th order linearization scheme? Well, it turns out that 0th order linearization is a perfectly suitable candidate to actually preserve these structures in the covariance models. So all 0th order methods can be plugged right into this, and we can actually implement 0th order solvers in linear complexity in the dimension. First order methods are a little bit harder, so there we need to be a little more restrictive. For example, if we're talking about Taylor approximation, then we need to assume that the Jacobian is diagonal, or we need to approximate it as diagonal. which is possible with this world of Hutchinson's trace estimators, but it's an assumption. It's a restrictive assumption which may or may not be useful for a problem at hand. So back to the problem. This is where we were before, and now if instead of using some dense covariance structure, so we have all the correlations and we have first order Taylor series linearization, we move to some isotropic, so some Kronecker structure, and we use zeroth order linearization, then we're suddenly at a solver that is maybe as fast as Daum and Prince. Maybe if you spin a little bit, you can see that it's a little bit faster as well. And that might seem a little bit petty, but in my view, that is a massive success of probabilistic ODE solvers, that we actually managed to get from something that was 10,000 times slower than a non-probabilistic method to something where we're actually competing in this work precision diagram language with non-probabilistic methods. So one thing that has to be said about this diagram is that we're not quite playing a fair game here. So I mentioned that the Pleiades problem is 14-dimensional. Yes, it is, but it's also a second-order ODE. So we have a second time derivative involved, and there are two ways of solving second-order problems. The first one is what I've shown earlier. We just have a different constraint, but we're tracking the second time derivative in our state anyway, so we might as well just use that one. So that is our constraint. That's the problem that the probabilistic solver sees. That is 14-dimensional. On the other hand, you can always transform high-order ODEs into higher dimensional first-order problems. So the same trick of stacking our states and derivatives that we did in the STEs, you can also do on the ODE level. And then you can use some black box or some off-the-shelf first-order solver, which is usually the common form that is assumed, like say SciPy or whatever. And then you can solve those. But that also means that the ODE that Daum and Prince sees is 28-dimensional. And twice the dimension, of course, has a big impact on the performance of the algorithm. So in some sense, it's a little bit unfair that we are solving the second-order problem directly, whereas the non-probabilistic solver can't do that. But then, if there were a second-order solver somewhere in JAX, then I would use it. But there isn't. So, yeah? Yes.
From my understanding, wouldn't the ODE solver have now 4 times 14 dimension in this case?
Yes, so the state dimension is higher than the ODE dimension. When I say 14, I mean the ODE dimension. The state dimension is the number of derivatives plus 1 times the ODE dimension.
So if we transform the second order problem into first order to solve it in Daum and Prince, it would be 28 dimensional, so to say.
Mm-hmm.
But and then if we solve the second order problem directly using the probabilistic solve of order 5,
Mm-hmm.
it would be 48 dimensional, right? So it's kind of still
That was some quick maths, but yeah.
right.
Yeah, so like, yes, that's true. So our state dimension is larger than, in this case, 14 or 28. But turns out that it's still sufficiently performant. So yeah, but yeah, maybe that makes the game fair again. I don't know. It's a good point. Yeah? Great, so now there's about 5 minutes left. That's good, because now let's go to the interesting bits. Maybe some of you are actually here to discuss precisely this problem, which is parameter estimation. So one common application of ODE models is to find out what the parameter of a dynamical system actually is. So we have an ODE again. Yeah, we also have some initial condition. Let's say that one is known. But we don't know what our parameter theta is. And since we're in machine learning, or many of us in machine learning, one common example is the neural ODE. But we don't care about neural ODEs, we care about parameter estimation. So what are we doing with parameter estimation? We have a lack of knowledge, we don't know what theta is, but instead someone gives us a lot of observations of our solution. And conveniently, those observations are on the same grid as our ODE solution. That doesn't have to be the case, but it's a lot easier for notation. So what are we doing with these observations? And how can we estimate our parameter from these observations? Well, let's say our posterior distribution is called mu. So it's a function of y conditioned on theta, the ODE parameter. And that's just the ODE posterior. So y conditioned on the constraints, the initial condition, and then we have sigma, and we have this theta parameter. And yes, our posterior actually has the state derivatives as well, but it's Gaussian, so we just marginalize them out and we throw them away. We want the distribution over y. And what are we doing with this posterior? Well, now instead of just evaluating our Gaussian likelihood of our observations at this mean of this approximation, we have a whole distribution to work with. So we can actually average the likelihood of our observations for basically all possible ODE solutions according to our model, which has a couple of interesting implications. The first one is that if our ODE solution, say it's really bad, if it's really bad and we use it for parameter estimation, then parameter estimation is going to be really bad. However, if we have these means of expressing this bad solution in, say, some covariance, then this process of averaging our likelihood over different realizations of our solution takes into account what might be wrong with our models. So we actually get something that's a lot more useful than if we just plugged in either the mean of this solution or some non-probabilistic solver. That is the first point. The second point is that since we already have some probabilistic description of our posterior, we can do some, say, slightly more exotic things. For example, we can assume that our observations are noise-free. What if our observations are noise-free? Then there's no real likelihood to evaluate unless we have a probabilistic solution. So just like we have those deterministic constraints on our process y, we can also see what is happening to our observations q given y without noise. And in this context, it's super boring because that's exactly the distribution of y. So we still have some likely information, but any linear transformation would be fine. And once we have these, then we can plug these, say, informed evaluations of our likelihood functions into, say, some Hamiltonian Monte Carlo method, and we can sample from our parameter posterior, and we can kind of see how, if we're looking at probabilistic solvers in the top row and non-probabilistic ones in the bottom row, if our solution is bad, then the concentration of the posterior is not where the true parameter is, and only for really small steps in the ODE it gets closer, whereas if we're looking at a probabilistic solver, then the center of this likelihood is still off. Yeah, okay, I mean, we can't change that, but at least we can inflate the likelihood so much that we can always include the truth as some reasonable sample from our parameter distribution. And another thing that non-probabilistic solvers just can't do is we are treating the ODE parameter as some parameter involved in the conditional distribution of our ODE solution. But we also have other parameters, say the sigma that defines the scale of our Wiener process that drives the whole thing. So we can also just treat those two together as two unknown parameters of our problem. We can optimize them in the same way. And interestingly, by including some extra dimension into your parameter space, sometimes optimization becomes easier. So here we're looking at the likelihood landscape of, I think it's a pendulum. So we have one parameter, the pendulum length, and we have one ODE parameter, the diffusion, which is this sigma that we were talking about. And while our optimizer would probably have a hard time going directly from here to there, by having this extra parameter that takes this detour, we actually have a much more tractable optimization problem to solve. Okay, so parameter estimation, really useful. In conclusion, interior Wiener process priors are really useful if you want to estimate probabilistic ODE solutions. Whenever you're discretizing in time, you should at least consider doing it adaptively, especially when you're doing initial value problems, because for many problems, that is just absolutely mandatory. And I know there were a lot of different concepts about implementation, and there was Taylor differentiation, there were QR decompositions, and so on. The main point is that if you want to wonder about implementation of probabilistic ODE solvers with high order integrated Wiener process priors, just take Taylor series perspectives seriously and see what happens to your Taylor coefficients if you transform them, if you move them around. And of course, very unbiased recommendation if you want to do parameter estimation. Now you know what to use and what not to use. So what's next for you? So now there was kind of the tour de force over what has happened, or like over some of the stuff that has happened in the past couple of years here in Tübingen. And the next step, in my opinion, would be to move from here to partial differential equations. So there has been work on generalizing these solvers to partial differential equations, time-dependent ones, but there's also been a lot of work on stationary PDEs, also from a Gaussian process perspective. This is very closely related to latent forces as well. Simo's already mentioned that. Simo has said that, yeah, they're just related. I kind of agree. They don't really fit into the storyline of this talk, but have a look, very important. And of course, there are lots of other ways of defining probability distributions or some statistical description of numerical differential equation solutions. So, there's a lot of stuff. Let's finish with pointing you where to go from here. So either you're all really keen on going through the QR decompositions and auto-diff variations, or you just use some of the code that already exists. And which one to choose mostly depends on what you like. So we have code in NumPy, we have code in JAX, and we have a lot of code in Julia as well. If you want to hear specifics, then talk to one of the Tübinger locals later, and I'm sure we're going to be happy to point you to many resources. And what can you do now? So like the one thing that would be great if you considered actually doing from here on is to take all of this knowledge about, okay, there are these ODE solvers, yeah, they're kind of cool, but oh wow, they actually work really well. So next time when you're solving ODEs or when you're doing something with simulation, at least think about exchanging some non-probabilistic solver with a probabilistic one. All right, thank you.